Hi, once again, thanks for tuning in to the pre-lecture video. And today we're talking about math. So section 1.4, math counts, everybody's favorite subject, right? So don't be intimidated because we're really going to explain things pretty thoroughly. And if you've already read the chapter in the book, you've probably got a pretty good grasp on things. Okay, 1.4 math counts. Whenever we are talking about numbers, we think of a universal system, right? Well, when we are biologists, chemists, or nurses, we are relaying information in numbers that are in amounts, units. So like a pharmaceutical in this amount, for example, or these cells in that amount, that is represented by a number and the amount is in a unit. And just like the number is in a universal scale, a universal language, that's math, the unit needs to be universal also. The rest of the world, even in their homes, when they are talking about what's the size of the container of the milk they bought, they are not speaking in the household terms that we use in the United States. In other parts of the world and in the system that we're going to use, they use for mass a kilogram, right? So they talk about grams and kilograms, and we're talking about pounds. Whenever they talk about volume, they're saying liters, and we're talking in gallons, cups, right? Whenever other parts of the world are usually talking about meters, and these are, just people that are not necessarily scientists. We're talking about, miles. Oh, so that's like a kilometer, right? That's that equivalent. This is the metric system. That's what the rest of the world is using, right? So the whole rest of the world. It's a terrible drawing of a globe. But anyway, so Système International d'Unité, SI. So that's the modern day version for the metric system, all right? And the reason that this system is used is because gallon, cups, teaspoons, it doesn't convert that well in the type of math that you're going to need to do, and you're going to see that quickly. The metric system uses units to where a base unit can have a prefix applied to it, and that changes the meaning by powers of 10, right? Powers of 10. So that's like 1, 10, 100, 1,000. That's powers of 10, right? And we can see in this table exactly what I'm talking about. So here we see the metric system, basically. This is always going to be something good for you to refer back to. Because it might take some time to really sort of understand this because you're so used to speaking in terms of gallons and cups and miles, right? And we're not used to using kilo, mega, giga, right? And deci, centi, milli, micro, and nano. Here's our base unit, okay? Our base unit in the middle of the screen. We might be talking about mass. And the unit for that in the metric system is gram for volume, liter for length, meter. You can apply these prefixes and easily convert the unit to something that makes more sense. Like, for example, say we are talking about meters. We could say 1 billion meters, right? Or we could use prefixes. See here, they get bigger. These are bigger, and these represent smaller quantities. Okay, and you're multiplying and dividing, right? For example, in 1 gigameter, there are, write it out again. It's just so cumbersome, right? 1 billion meters. So instead of talking about 5 billion meters, you can just say 2 gigameters, right? That makes more sense. And think of this way. There are 10 deciliters in 1 liter, okay? And vice versa. There are 100 centimeters in 1 meter, right? Y'all are familiar with the meter stick? See, you've had some exposure to the metric system, I know it. Whenever we're talking about these, relationships between those numbers, those examples that I gave you are called equivalent units, right? It means just that quantities that can be related to each other by an equal sign or equivalent units. So here, 1 deciliter, and get familiar with the abbreviations here too, just like the elements, is equal to 1/10 of a liter. Makes sense, right? So 1 deciliter, that's smaller than 1 liter, right? It takes 10 deciliters to make 1 liter, right? This is 1/10 of a liter. So 1/10 of a liter equals 1/10 of a liter. You see what I'm saying? And as I mentioned before, so 10 deciliters equals 1 liter. And there's something interesting that you can do cool with these numbers that's really important to the math and the type of problems that you're going to need to solve. So these equivalent units can be used as conversion factors. So these are magical. All you have to do is write one over the other like a ratio. 10 deciliters over 1 liter. So equals 1 liter over 10 deciliters. You see, it cancels out, right? So basically, what you are doing here is you are going to be multiplying by 1 to convert to a different unit. So you can use this to multiply by 1 to convert to a different, abbreviation there, unit. Okay. And you can think of it so like this. Everyday terms, 1 dozen eggs or 12 eggs. Okay. Or let's say 13 donuts. 1 baker's dozen equals 1 baker's dozen over 13 donuts. If your problem gives you a number in donuts and not a baker's dozen, then you can use this conversion factor. If they give you donuts and you want the answer in baker's dozens, you can use this, okay? Conversion factors allow you to convert a quantity from 1 unit to the equivalent quantity in a different unit, okay? And this whole relationship that we've been talking about is referred to as dimensional analysis. Remember, keep your definitions straight. You never know when you're going to have multiple choice or matching on the test. And this is important. People are going to talk to you about this in the future. Know what dimensional analysis is. Okay? Impress your friends. And when we're solving the problems that we're going to solve in just a minute, and some of them we'll solve in class, you can use these 3 steps that are written right here. So first, determine the units on your final answer. So think of this as like Google Maps. You're trying to find directions to the concert. Right now, you are at home. So where do you want to go? So where are you going? Then, second, establish the given information. So what do I have? And how do I set up the problem? or basically see, what do I have? Let's think of this other one like this. Where am I going? Well, no, we're good. Establish the given information. What do you have? Think of it that way. In step 3, decide how to set up the problem. Which conversion factor should be used to leave the desired unit in the answer? Okay. All right. So determine the units. Where are you going to? Establish the given information. Where am I at right now? So sort of like a map. Think of it that way. What do I already have? Where am I at? In step 3, decide how to set up the problem. So how am I going to get there? That's your route. How am I going to get there? Sorry if that was a bit confusing. And your last step. Get there. Do it. Plug everything in. Okay? So if you think of it in these 4 simple steps, it doesn't seem that bad. Where are you going? What do you have? How are you going to get there? Then just get there. And whenever you are reporting your answers, your final answers, we need to keep in mind a certain number that is very precise. It's certainty. So measuring matter relies on the precision of the instruments that we use to measure it. So you have to use an instrument that's calibrated. It's based on some standard, right? Just like the metric system, a standard. And, you know, these measurements that you're going to get only have a certain certainty. They only have the certainty that they really define. And that determines the significant figures. Like, for example, if you ran down 3 streets and you said, I ran this many feet, and you wanted to report that to 5 decimal places, that doesn't really make sense. Do you think that that precision is really true? You know, so it's important to report calculated answers reasonably, right? It's not reasonable even to report if you ran 3 streets in a certain number of feet and down to the inches. Okay, it is not really, it's not really telling us anything. How true is that? What is the precision? So when reading a measurement from a non-digital device, there's some level of uncertainty. And the significant figures are the digits known with certainty plus 1 estimated digit. So basically, you don't want to try to report more information as totally valid than what really is, generally speaking. I know it's a little bit confusing. But you can only report what is really certain. In digital devices, such as your thermometer, you know, they give you the number of significant figures in the digital readout, okay? That's what is certain. They give you the number of significant digits that is certain. So they'll give you, you know, 4.5 Fahrenheit. Oof, that's a high fever though, okay? But this is typically what the readout is. They don't know for sure if you have 104.51, but they can tell you with certainty you have 104.5. Okay, in any measurement, all non-zero numbers are considered significant. All non-zero numbers are considered significant. So if you're reporting a non-zero number, people are going to think, wow, that is a really close measurement. That person knows that that number is true. Okay, that's what's important about significant figures. You're saying how certain you are that that measurement is that number. Okay, so you want to be careful with this. And we're always going to report answers in this class with the correct significant figures. Therefore, you really need to have this foundation pretty strong. So significant figures usually become problematic for people in the context of zeros. Those are the troublemakers. Even Pearson textbook admits that these are the troublemakers. So if a zero and a number without a decimal point is significant, that can be shown. You can show that the zero is significant by putting a decimal point after that zero. So if you write this ordinarily, that's one significant figure. But if you want those zeros to be significant, you just put a decimal point after it. Okay. To indicate significant zeros in large numbers, you draw a line over the significant zero, above the significant zero. Like large numbers, draw a line above the significant zero. Exact numbers, or numbers that used in defined conversion factors and counted items, are exact numbers with an infinite number of significant figures. Okay. Let's go through some of these rules about significant figures and zeros. That'll kind of help to clarify all of the jargon that's out there so far. Here we have this table with these examples, and I think this is really going to help you out to visualize all of that math, written language, verbology. So a digit is significant, okay? A digit is significant if it is not a zero. So here you see 1, 2. You have two significant figures. Okay, it's not a zero. Here, 1, 2, 3. Not a zero. Okay. A zero between non-zero digits. Well, this one's between non-zero digits, so 1, 2, 3. Because we know that if it's non-zero, it's a significant number, right? We've already gone over that. This is 3, right? This is in the middle, 1, 2, 3, 4. They're all. So here, a zero at the end of a number. What? It has a decimal at the end. So 2. Here, we have a number with a decimal, okay? Even though it has a zero at the end. So 1, 2, 3, 4. All right. A zero is not significant if it is at the beginning of a number with a decimal point or in a large number without a decimal point. And let me show you a trick for that. You might think it's kind of a silly trick, but so it's whatever works. You don't have to use it, but it works. Okay. I really am an artist sometimes in my spare time. This is a really silly sketch of the USA, and everyone wants to come here on vacation. All right. So keep that in mind. So that's what this is. All of the people are crossing the Pacific and the Atlantic to get to the USA for a vacation because we have a lot of cool things going on. So Pacific, think of, that's if the decimal is present. And here, the decimal is absent. So, for example, here it's present, right? There's the decimal. So you draw the line coming in from the left to the right, and you have one significant figure. Do it again. Is the decimal present? Yes, it is. So draw this way from the Pacific towards the US, right? Two significant figures there. All right. Is the decimal present there in B? 12,000 kilometers. Well, it's not present. So we're going across this way. Atlantic towards the US, 2. Is it present? No. So we're going across the Atlantic towards the USA. There, 3. You don't have to use it, but it might help you out. Whatever helps. Okay, so calculating numbers in rounding. Adding, subtracting, multiplying, and dividing they can result in numbers that seem more certain than they are. If you think of a speedometer that gives you a number, I don't know. You know that whenever these kinds of calculations are made, that those numbers are not all necessarily really true. Or if you put something in a calculator and it gives you a reading like this, manipulating measurements with arithmetic does not really increase their certainty. That's just arithmetic, okay? It cannot be, an answer cannot be more certain than the least certain number in the calculation, okay? And there are some rules for that. There are rules for addition and subtraction, and then there are rules for multiplication and division. It's different. Be careful. So keep separate and keep in mind whether it's addition and subtraction or multiplication and division. If you don't, then you probably get the answer wrong. So the answers for addition and subtraction should match the least number of decimal places in the measured numbers. Okay, the least number of decimal places. So least decimal places given in the problem that you're trying to solve. Whereas with multiplication and division, it should match the least number of significant digits in the measured numbers, okay? So the least, this is my abbreviation for significant digits, SIGDIGS, in the measured numbers, okay? Oops. So some of the rules for rounding numbers are, if the leftmost digit to be dropped is 4 or less, simply remove it and the remaining digits. So let's see, like an example for you. So if it's less, so I mean like 3.246, if it's less than 4, simply remove it in the remaining digits. But if the leftmost digit to be dropped is 5 or greater, increase the last retained digit by 1 and remove all the other digits. So here, versus 3.5426. So if it's a 5, it's 5 or greater, you round up to 4. So this 3 becomes 4. Okay. For rounding a large number with no decimal, substitute zeros for numbers that are not significant. And we're going to have examples of that in the problem. So in the problems that we're about to do. If rounding a large number with no decimal point, substitute zeros for numbers that are not significant. All right. And make sure that, well, let me just show you an example here. So 35,462. Okay. And so if you're really only supposed to be giving 2 significant figures, if you determine by your problem that that's really all the certainty that you have, because there's only 2 significant figures in one of the measurements that you're given, then you need to report this just as, see, because this is a 4, so it's less than 5. And so you're just substituting zeros for numbers that are not significant. Okay. Whenever you're doing a multi-step problem, do not round at each step. This is going to be cumbersome and it's going to produce incorrect responses. Right, so don't do any more than you have to do. Don't start rounding until the end. So another thing that we do, speaking of large numbers, is to write numbers in scientific notation. And you've probably seen this before, but maybe you didn't know exactly what it meant. The general form for scientific notation is, so if you have, for example, C times 10 2, n. Okay, so C is the coefficient here, all right? And it's always going to be at least 1, but less than 10. N is the exponent telling us the number of tens places that apply, okay? So a positive exponent tells us that the number is between 0 and 1. So if you have, for example, 1 times 10 to the 2, this is going to be positive, okay? Because this 2 is positive, all right? And so that tells you the number of tens places that apply. So, right? So, and basically, and you'll see this is 10 times 10. So 100, okay? You're moving the decimal twice for that coefficient number. So that's 100. A negative exponent tells us that the number is between 0 and 1. So let's see, you have 0 times 10 to the 2. So here you have the 1. You know, the decimal is really always right here. So 1, 2. And so you are then writing this. So you have this. In scientific notation, only significant figures are shown in the coefficient. All right, so only one significant figure here. So here we have our 1, and here, you remember, we have our 1. All right, so I don't know why all of the numbers are missing on this slide. They should not be. But I will make sure that when this slide is posted for you on Moodle, that all of these numbers are here. Just know that, for example, I'll give you a few more examples here. That you have, this is basically 1 million is 1 times 10 to the 6. So a lot of instances where we'll use the scientific notation, I've come from a microbiology and immunology background. So if we're going to be using a certain number of fungi in an experiment, the number of fungal cells there, we want 1 times 10 to the 6 cells per mil. That's normally what we would say, 1 times 10 to the 6. We're not going to be saying 1 million very often. It's useful to use the scientific notation. It's more professional. This is how we write it in the publication. It's how everybody communicates, even though we know it means 1 million, right? Because that's a pretty big number. So it's easier to use the smaller coefficient number, right? And just include the exponent. We could say 1 times 10 to the 6, 1 times 10 to the 5th. For some reason, it's easier to picture. And this is 10 times 10 times 10 times 10 times 10, what? Times 10. 1, 2, 3, 4, 5, 6. All right. And so, you know, it's probably even good for you to fill out a very similar table like this, because so on and so forth. You know, right here, you have 0.1. So this is just 1 divided by 10. And this is 1 times 10 to the negative 1, right? So you really have all the knowledge and tools to fill this table out, but on Moodle, I'll have the table all the way filled out. Okay, percents. You're probably familiar with hearing about percentages, like a 50% sale on strawberry Frosties because they're new and they want people to buy more and try it out. So 50% of what? The total price, 100% of the regular price, 50% of that. So it's percent is represented by the symbol, the percent symbol here. And it means that the part out of 100 are total. So 50% of the price, let's say, out of 100% out of 100, which is 100% of the price. So, or hundredths. Percent allows us to directly compare two sets of numbers that have different total sizes. So let's say you are a farmer and you grow apples and bananas and you sell them to a grocery store, and you have apples and you have bananas, and you got a report back from the farmer, and he said, well, let's say, okay, you gotta, let's say that the grocery store calls you, the farmer, and tells you that 25% of their apples that you gave them are rotten, and 50% of the bananas are rotten, right? Well, it's really, this gives you a different type of information compared to whether if, what would be the next question that you would ask? Well, 50% of how many? So 50% of, let's say, we'd say, well, how many bananas did you buy in the first place, and how many apples did you buy? Because otherwise, that could mean that maybe 50 out of 100 bananas are rotten. And he'd say, oh, well, just 2 out of 4 bananas, that's so that he'd say, I have a total of 4 bananas. So that just means that 2 of your bananas are rotten. If he says 50%, half, you have to be able to convert between these numbers, okay? For those reasons, you have to understand the differences between total numbers and percents. Let's say 25% of the apples are rotten. Oh, how many apples do you have? Well, I have 4 apples. So just one of them is rotten. So that makes a big difference. Whereas, maybe if you had 100 apples, then that would mean 25 of those apples are rotten. So the percent is, it gives you a certain bit of information, but it doesn't tell you totals without you knowing what that 100% total number is. Okay, just to give you a little reference, a fraction can be converted to a percent by dividing the numerator by the denominator, multiplying by 100, and adding a percent sign. All right, and we're going to do some examples of that. But basically, what you have is, let me get rid of all this. That might even just be a little bit too much, but I'm just trying to show you what a percent of a total is. So you don't always have 100 as the total, right? Percent, let's put our percent sign, is equal to part over the whole times 100. Right. So here, if you have 2 out of 4 times 100, so you have 0.5 times 100, this equals 50%. Okay, so like I said before, if these were like bananas, 2 out of 4, that's 50%. So 2 divided by 4, 0.5, half, times 100, that's 50%, right? There you go. That's a much easier way to think about it. A decimal number can be converted to a percent sign by multiplying by 100 and adding a percent sign. Okay, so basically, let's just do the flip of what we just did. So 0.5 times 100, right? So just think you can move that decimal place 2 times, 100, right? Hundredths, 2 places, 50%. So that's all there is to that. It's really not super complicated. And I think this is it. 1.5 is for the next video, and we're going to work some of the in-class problems, the in pre-lecture problems, and you're going to do the even problems in class. So here we go, 1.17. Give the number of significant figures in each of the following measurements. 25 minutes. So these are non-zero numbers, these two, right? So that's 2 significant figures, right? Everybody on the same page? All right, here. So we have a decimal. Okay, so we're coming in this way. We have 4 significant figures, okay, right? So here we have another decimal, so we're coming across this way. So we have 1, 2, 3, 4, 5. So we have 5 significant figures, right? Because we have a decimal. And so if you remember our little map of the United States, right? The USA, Pacific, they're all coming in that way. Atlantic coming from vacation that way. So P present, it's present, you're coming in that way. So you have 1, 2, 3, 4, 5. You see that? Okay, so here we have a 0 number that has a decimal at the end. So that means this 0, it really is a significant 0. So here we have 3 significant figures. Okay. 1.9. Complete each of the following calculations and give your answer to the correct number of significant figures. Okay. All right, so we have 100 times 23. So this would give you, right, 2,300, but you're using what? Multiplication. And so you need to look at what? The number of, the least number of significant figures that you're given. Okay, so look, what's that? 1. So you're just going to, so this is 3, so it's not greater than 5, that's just 2,000. So 2,000, this is the answer that you want. Okay, 97.5 minus 43.02, this is 54.48. Okay, and so this is subtraction, right? Always look at the operation that you're using. And the least number decimal places is 1. So you only want 1. Therefore, this is 8. So you're going to round up. It's going to be 54.5. Makes sense? Okay. C. 8,064 divided by 0.0360. Okay. This is going to give you a big number. And how many decimal places are you going to use? You're dividing, so you're going to use the least number of significant figures. So here's a decimal. It's present, going across, going on that way from the Pacific. So that's 3. So this significant figure is going to be written 224,000. Okay. And then D. 54.00 plus 78. Okay. This is addition, remember? So what is the least number of decimal places? Well, here you have 2, but here you have none. So no decimal places. So your answer is just going to be 132. Just the non-zero whole number, okay? So well, you're not going to have any decimal places, right? You're adding. Okay, so 132. That makes sense. All right. 1.21, an allied health question. I like these because these are really more applicable and less abstract. A typical aspirin tablet contains 325 milligrams of the active ingredient acetylsalicylic acid. Convert to grams. All right. So what do we have? Remember our steps? 325 mgs. Okay, so we have mgs here, and we're wanting to convert to grams. So what are we going to use? our conversion factor, our magical conversion factor. That's your friend that's going to help you out. And so you have 1,000 milligrams in 1 gram, right? Because you want to convert to grams. Your answer is going to be in grams. Okay. So basically, you can cancel these milligrams, and it's going to be like 325 divided by 1,000. So your answer, you need to give in how many decimal places? 3 is going to be 0.325. Okay, that 3 significant figures. So that is going to be your answer. Okay, that's a G. Sorry if my G doesn't really look like a G. All right. 1.23. Write scientific notation for the following numbers. Okay, on A, 203 million. 203 million. Okay, that's a really big number. So we're going to put that in scientific notation. And it's going to be more relevant when communicating with other scientists, other nurses and doctors, right? For whatever this number represents. So what are we going to do? Well, I like to do like this. I like to draw it out, okay, over the zero. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Because this coefficient, this is how we determine what's the coefficient. It's going to be between 1, it's going to be between 1 and 10, right? So it's going to be 1 or more but less than 10, right? So here you have 2, so here's where you're going to put the decimal. 2, that's going to be your coefficient, times 10. So we're doing, it's powers of 10. So 10 to, how many times did we go over? 1, 2, 3, 4, 5, 6, 7, 8. 8, and that's positive because that's that's bigger, right? Okay, it's not less than 1, it's bigger, right? Okay, so 2 times 2, oh, no, that's not right. Why is it not right? Because you can't just ignore that 0.03 times 10 to the 8th. Okay, B, 12.4. Okay, so this is positive because it's going to be still bigger than 1, but see, we have 1. Like I said, it can be 1 times, it would be 1.24 times 10 to the, how many times did you move it over? Just 1. So if you move it back, it's going to be the same exact number. So here you have 1.24 times 10 to the 10 to the power of 1. C, 0.000000278. Okay, nobody wants to communicate something that way. So let's see, we'll move it 1, 2, 3, 4, 5, 6, 7, 8. So 2.78 times 10 to the negative, what number did I say? 8. There you go. And it's as simple as that. Okay. 1.25. Express the following numbers in decimal form. So really, all that you're doing is moving the decimal. So that's 1, 2, 3, 4, 5. So you're going to put 4 zeros. 1, 2, 3, 4, 1, 5, 6. Right? Right? 4 zeros. Okay. And that was to the left because we have this minus sign. Left, minus. Just remember that whatever way you can. You have a minus, you would move the decimal to the left. Left, minus, Linus. I don't know. That's really silly. Whatever kind of acronym or mnemonic or silly tool you want to use, that's fine. So B, 2.8 times 10 to the fifth. So you're going to move to the right because it's positive. So you're going to move the decimal to the right. Okay, 1, 2, 3, 4, 5. So that's 4 zeros. So 2, 8, 1, 2, 3, 4. That's 280,000, right? Okay. Let's see. Let me make sure that I did this right. Oh. Okay. 1, 2, 3, 4, 5. Right. Okay. Right. So C, 9.0 times 10 to the negative 2. Remember, negative is to the left. Okay, whatever you need to do to remember that. I can try to come up with a mnemonic device for you besides that silly one that I just came up with. Left minus Linus. So 10 to the negative 2. All right, so let's move this decimal place to the left. 1, 2, 0.09. And be careful because even I can make mistakes adding zeros. That's sort of like almost like a monotonous task that you can easily write down the wrong number. And so here you're going to write down, you want two significant figures, right? Because you have two significant figures that were in your number here, 9.0. So 9.0.090. So you need two significant figures. Got to remember. So did we do that with our other problems? Yes, we kept that. Okay. So 1.27. Allied Health. Write scientific notation for the following numbers. A platelet dose of 500 billion. If you had to say that all the time, it would become pretty cumbersome. So normally what you would read in a lab report and a blood work is scientific notation. So see, it's really important that you memorize that. You not just memorize this, you learn this because you're really going to have to use this in your career for the rest of your life, not just arbitrary. A platelet dosed. And platelets, that's pretty important, right? What's going on there? Coagulation. You know, so how are you going to write this scientific notation? So let's see. Whenever it's zeros like this, you can easily just say 3, 6, 9, or it doesn't really matter what numbers there are, 3, 6, 9. Just whenever you see the commas of 3 like that, 9, 10, 11. So 5, just 5 times, yeah, because there's only one significant figure there. 5 times 10 to 11. A red blood cell count of 5,500,000. Okay, so 1, 2, 3, or you could just go 3, 6. So that's 5. And so you have two significant figures, 5.5 times 10 to the 6. So in your coefficient, use the right number of significant figures that you got in your problem, the number that you were given in the problem. Okay. 1.29. Express the following numbers as a percent. Okay. So how are you going to do that? All right. 1 out of 4. And we kind of talked about this a little bit before in the example that I gave. This is going to be what? So 1 divided by 4. So, you know, take out your calculator. You can do 1 divided by 4, which is going to be 0.25 times 100. That's 25%, or we call that 1/4, right? So 3 divided by 8. That's all you have to do. So that's 0.375 times 100. That's going to be 37.5%. Okay. But we're going to have to round this, usually as percents. We round this, and our question says report to two significant figures. So this is a 5. So what is the answer? 38%. Okay. See, always read all of the directions. All right. So 66 divided by 100 is 0.66 times 100. And that's going to give you 66%. That's already two significant figures. So that's all your answers for 1.29. Okay, let's see. We're going to do 1.31. We're going to go ahead and do this one. We're getting there. We're almost done. All right. 1.31. Okay, express the following numbers in decimal form. All right, so let's see. Okay, 4.5%. So, basically, let's see. How do you get to 4.5%? Let's see. You would get that if you did 45 divided by 100, right? Oh, so you're trying to get 4.5% into decimal form. Okay, so you have 4.5 divided by 100, and that's going to give you 0.045. Okay, does that make sense? So you're going to have 13.0 divided by 100, and we're going to keep with the significant figures. Okay, so that's 0.13, and you have three significant figures, so 0.130. Okay, that's your decimal. Here, 66 divided by 100. Okay, and so that's going to be 0. You have two significant figures, 66. And you're going to have 78 divided by 100. And that's going to give you 0.78. That's your decimal. Okay, right? And if you move the decimal back, as if you were multiplying by 100, and then add a percent sign, then you get the percentages. Okay, it works the same way. You can just go back, toggle back and forth between the decimals and the percents. All right, so I think that's actually where we are going to stop for the day. So thanks for tuning in.